This video is brought to you by mywayteaching.com.
Specific heat capacity. That the first monoatomic gases, specific heat capacity in case of monoatomic gases. See, the molecule of a monoatomic gas has only three translational degrees of freedom. There is no rotational degrees of freedom in case of monoatomic gases. Thus, the average energy of a molecule at a temperature T is given by at the temperature T is given by 3 by 2 kb into T. Okay. So the total internal energy of a mole of such a gas is given by it is represented with U 3 by 2 kb into T into Na for a mole, that is given by 3 by 2 into RT, isn't it? The molar specific heat at constant volume, that is represented with Cv. So this Cv, that is molar specific heat at constant volume for monoatomic gas, we can write it as du by dt, that is 3 by 2 RT. So we already know for an ideal gas, Cp minus Cv is equal to R, where Cp is the molar specific heat at constant pressure. That Cp is given by 5 by 2 R. The ratio of specific heats, that is given by gamma, which is given by Cp by Cv, isn't it? So that Cp is, we already know Cp is 5 by 2 into R. RT, and that is 3 by 2 into RT get cancels and we get 5 by 3, isn't it? So this is the ratio of specific heats. This is for monoatomic gas. Now let us see for diatomic gas. See, a diatomic molecule is treated as a rigid rotator, isn't it? Okay, like a dumbbell has 5 degrees of freedom, 3 translational and 2 rotational. So using the law of equipartition of energy, the total internal energy of a mole of such a gas, we can write it as total internal energy. So here diatomic gases have both translational as well as rotational degrees of freedom. So the total internal energy is given by 5/2 kBT into Na, that is 5/2 RT. The molar specific heats at constant volume for this diatomic gas is given by 5/2 R, and Cp is 7/2 R. So the ratio of specific heat for this rigid diatomic gas is given by 7/5, isn't it? If this diatomic molecule, if it is not rigid, but it has vibrational mode energy term, that is also added to that total energy term, isn't it? So in that case, we can write the total internal energy as U is equal to 5/2 kBT plus kBT into Na. Okay, that vibrational energy term is also added to the total energy term. So molar specific heat at constant volume is given by 7/2 into R, and Cp will become 9/2 into R, and gamma will become 9/7 into R. Okay. Now let us study in case of polyatomic gases. See, in general, a polyatomic gas has 3 translational, 3 rotational degrees of freedom, and even a certain number of vibrational modes. It contains all 3 modes of energy. So according to the law of equipartition of energy, for 1 mole of such a gas, that internal energy is given by 3/2 kb into T plus 3/2 kb into T F kb into T into Na. So here at constant volume, molar specific heat is given by 3 plus F into R, and at constant pressure, molar specific heat is given by 4 plus F into R, and that ratio of specific heats will get as 4 plus F by 3 plus F, isn't it? Yes. And Cp minus Cv is equal to R. This is true for any ideal gas, whether it is monoatomic gas or a diatomic gas, or even it can be a polyatomic gas, but this, it remains true. Okay. See, in this table, it summarizes the theoretical predictions for specific heats of gases ignoring vibrational modes of motion. Okay, and these values are in good agreement with experimental values of specific heats of several gases. Okay, so this is predicted values of specific heat capacities of gases. So they have given for monoatomic, diatomic and triatomic, and even they have given the ratio of specific heats, and they have given Cp minus Cv, and molar specific heat at constant volume, molar specific heat at constant pressure. Everything is given here. Okay, so here you can see the measured values of specific heat capacities of some gases: helium, neon, argon, hydrogen, oxygen, nitrogen, water, and CH4. This is a polyatomic. So they are given CV, CP. So they have given the even the ratio of specific heats: gamma, Cp minus Cv, molar specific heat at constant pressure at constant volume, the name of the gas and the nature of the gas, whether it is monoatomic, diatomic, or a polyatomic, that is also given. Okay. Now let us see a simple problem. A cylinder of fixed capacity, that is 44.8 liters, contains helium gas at standard temperature and pressure. What is the amount of heat needed to raise the temperature of the gas in the cylinder by 15 degrees Celsius? Okay, now we should find the amount of heat that is required to raise the temperature by 15 degree Celsius. They have given the constant gas constant value as 8.31 joule per mole per Kelvin. Okay, so now we should find the heat required. See, using the gas law, that is PV is equal to mu R T. So we can say that 1 mole of any gas at standard temperature, that is 273 Kelvin, and at standard pressure, that is 1 atmospheric pressure, occupies a volume of 22.4 liters, isn't it? 1 mole of any gas, that is ideal gas, it occupies a space of how much? 22.4 liters at standard temperature and pressure. This universal volume is called as molar volume. Thus, the cylinder contains 2 mole of helium because it is given as 44.8 liters. Since helium is monoatomic, its predicted molar specific heat at constant volume. Helium is monoatomic, so we can say Cv is equal to 3 by 2 into R, and we can write Cp as 3 by 2 R plus R, which is given by 5 by 2 R. Since volume of the cylinder is fixed, the heat required is determined by Cv. So we can write heat required is equal to number of moles into molar specific heat into rise in temperature. So here 2 moles of helium, isn't it? So number of moles become how much? Yes, number of moles becomes 2. And molar specific heat is given by 3 by 2 into R, that is 1.5 into R, and we should calculate heat required for 15-degree rise in temperature, that is given in the question. So multiplied with 15, we get 45 into R. So here in the question they have given the value of R as 8.314, isn't it? So we should substitute the value of R in the equation. So we get heat required is equal to 374 joules. Okay.